Testing on YouTube. YouTube works. All right, let me adjust this microphone. Adjust this pop filter. Get rid of that. Let's test on X. How's it going, Sarah? How's it going, Pratik? All right. Let's do the ritual. There's definitely a ritualistic element to this stream. All right, I think we're live on X. Let's double check. Broadcast is not available. Come on. Broadcast is not available. Oh, there we go. All right, it's working. Let's go ahead and get started. Nice cut, G. I mean, I just shaved my head. It's not really a haircut, but I've been cutting my hair for a long time at this point. How's it going, Aaron, NLP prompter? Let's get the stream started. All right, welcome everybody to another Hoopo stream. Today we're going to be doing one called Tiny Transformers. Transformers are going to be getting really small in the future. And we're going to be exploring some evidence that demonstrates that in some recent papers. How's it going, Mark B., Tuan, and Julien? So we're mainly going to be looking at 3 different papers here. This one came out on the 17th of October, 2024. This is called What Matters in Transformers. Not All Attention is Needed. It's coming out of University of Maryland and University of Maryland College Park. I guess that's where the University of Maryland is. We're also going to be looking at this paper, PYRAMIDDROP, Accelerating Your Large Vision Language Models via Pyramid Visual Redundancy Reduction. It's a completely different group here. This is Shanghai AI Laboratory, USTC, and CUHK, coming out the 22nd of October, 2024. And then the last paper we're going to be looking at is going to be this one here. This is 1-bit AI Infra, part 1.1, Fast and Lossless BitNet B1.58 Inference on CPUs out of Microsoft Research, coming out on the 21st of October, 2024. So slightly different papers, but I think they all point towards a very interesting development, which is that much like we're advancing in the field of making transformers and pretty much any model just smarter, right? So models are getting stronger and smarter, more intelligent, more capable over time. We're also seeing that these models are going to be getting smaller over time as well, which is, I think, makes the future very interesting, right? Because if we were in a future where the models got better, but they only got better with size, then, you know, in some ways that would be kind of depressing, because you would have a world with very big intelligent models that were controlled by people who had the resources to run those very big intelligent models. But it seems like we're simultaneously discovering that these models can be made smaller and smaller and smaller without sacrificing too much of that intelligence. So we're going to start with this one here, What Matters in Transformers. So on this one, this is a kind of like an empirical study kind of paper, right? So they really kind of old school science here of like, hey, let's mess with a bunch of different things and see what happens. And here they're going to be investigating redundancy across different modules within the transformers, including the blocks, the MLP, and the attention layers. So I have my good old visualization of a transformer here. This is a little bit older at this point. This is Nano GPT, but it's still the same basic architecture in all transformer models, where you have blocks, which refers to basically this repeated element here. So here you can see there's 3 blocks. And then you have, within a block, you have kind of the 2 components. You have what's known as kind of the attention map and the attention head, which is this kind of smaller part here. You can see there's multiple heads there. And then you have the MLP, or multi-layer perceptron, or feed-forward networks, which is kind of this part right here. Right? So in this paper, what they're going to be doing is they're going to be dropping out different parts of that, right? So dropping out basically just means deleting. So you train an entire transformer like this, and then you're going to delete different parts of it, and you're going to see which part is important and which part is not, right? So this is kind of like if you had, this would be highly unethical to do with humans, but you have basically a bunch of different humans and you cut out different parts of the brain, and then you see which, what type of capabilities the humans still have, right? So that's a way of determining which parts are important and which parts are not. It's kind of like an ablation study. So whenever they do block removal, they basically just remove entire blocks, basically like this entire thing here. If they do MLP dropping, they basically remove this MLP part. And if they do the attention dropping, they remove this attention. And they also kind of go into dropping sub parts of that as well. So these attention layers, a large portion of these layers exhibit excessively high similarity and can be pruned without degrading performance. Llama 270B, which is a little bit older of a model, but it still uses the same transformer architecture that we're seeing in all the different models, achieves a 40 or a 50% speed up with only a 3% performance drop by pruning half of the attention layers. So they literally remove half of the attention layers and get only a 3% drop in performance for a 50% speed up, which is quite impressive. Method that jointly drops attention and MLP layers, allowing us to more aggressively drop additional layers. So they also have their own kind of dropping techniques on top of that that allow you to go even more in the direction of trading off the size of the models for inference speed. Transformer-based language models have redundant architectures, leading to inefficiencies in deployment cost and resource demands, right? The bigger the model is, the longer the context, the more bytes you're using for every single parameter within that model, the more it's going to cost to train, the more it's going to cost to deploy and run in inference. So if you can find any way of making them smaller, you're going to save a bunch of money and you're going to be able to run them faster, run more of them in parallel, serve more people, right? And if we're moving into a future where everyone has thousands of requests per day because every single product that they're using has AI baked into it, and then even the AI that's baked into products is calling thousands of other AIs for every single call that you do, right? We're going to be doing a lot of inferences per person in the future, so we really want to reduce the inference cost. Transformers are multiple stacked blocks, each containing an MLP and an attention layer, which serve distinct functions and exhibit corresponding different levels of redundancy. So we need to identify and address which of those are the most critical. In block drop, we're going to observe that removing entire blocks leads to significant performance degradation. So that's kind of the first finding that they present here, is that when you remove an entire block like this, right? So like, let's say you just got rid of this middle block, you just cut out this whole block and you just feed what comes out of block 1 into block 3, you get a kind of a big performance drop. So naively just getting rid of these blocks, and for example, I think they say in the Llama 2 that they're using here, there's something like 32 blocks. So if they just cut a bunch of those blocks, it really doesn't work well. So instead, they're going to be separately pruning MLP and attention layers. Dropping the MLP or the FFN negatively affects performance, but dropping attention layers does not. Attention layers can be pruned without degrading the model's performance. Dropping more than 50% is comparable to the performance of the full model, indicating a high degree of redundancy in these layers. Okay. And then they do this joint layer drop, which I think we talked about. So let's look into specifically maybe their figure here, visualization of layer drop, where we visualize dropping either the MLP or the attention layer. So you have here your MLP, your layer norm. Layer norm isn't really shown here. Here they have it right here. But basically you're just taking the input that's coming from the previous layer and then you're just normalizing it, right? So you're taking what could be very big activations, very small activations, and the layer norm makes it all kind of nice and smooth, right? So that everything is a little bit more comparable, right? You don't have like super bright numbers. So you see here, if you scroll in, you have some that are kind of slightly gray and some that are really gray, some that are really green and slightly green. Neural nets don't like very small and very big things all jumbled together like that. They like them a little bit more uniform. So you can see that after you perform this layer norm, it's a little bit more uniform. If it's green, it's green. And if it's black, right? So it's not as kind of ambiguous as that. So you have layer norms before the MLP and before the attention. So attention drop is cutting out the attention, and of course you get the layer norm out of that for free as well. And in the MLP drop, you cut up the MLP with the layer norm. The way they're going to be determining what to drop is based on similarity scores. And the similarity score they're going to be using here is just cosine similarity. So I feel like most of you probably already know what cosine similarity is, but just in case there's some new people watching this is what cosine similarity is, right? In elementary school, you probably learned the different triangle relationships, and the cosine of an angle, right, will basically tell you this degree, this angle right here. And you can think of the representations in each of these intermediate points in any neural net as vectors in a high dimensional space. Here, this is MNIST, which is handwritten digits, and represented as two-dimensional vectors, right? So this dot represents one handwritten digit, and you can see it has it's some vector in this two-dimensional space, and you can say, okay, well, what is the cosine similarity between this and this point, right? And that'll give you a number, and that number is effectively kind of how similar those things are, right? So you can see here that if we took the cosine similarity between the numbers 7 and 9, most 9s are more similar to the numbers 7 than they are to the number 3, right? So that's effectively what cosine similarity is. And their intuition here is that if you have a bunch of redundant information, you don't need all of that, right? So neural nets are very good at kind of picking out the information that is coming out or coming from previous layers, especially these multi-layer perceptrons, right? Because multi-layer perceptrons or feed-forward networks, they have full connectivity, right? Every single neuron is kind of connected to every single neuron from the previous layer. So you don't need redundant information in there, right? As long as the information is there, the neurons that are connected to it, the weight for that will allow the neuron at the next layer to activate. So if you have features that are coming in and you have like the same feature 4 times, you can get rid of 3 of those and just have the feature once. And that's kind of the intuition that they use for using cosine similarity as a way to drop out redundant features, right? Let's see up here, drop layers with high similarity scores. And I think they also mention it here. I think let's go into the other paper here, because I think this will start. So we're not going to be talking about this paper, but this paper also was quite popular over the past couple weeks. This was called Differential Transformer, and this is kind of the same idea, right? So in this paper, transformers tend to over-allocate attention to irrelevant contexts. Differential attention mechanism calculates attention scores as the difference between 2 separate softmax attention maps. By canceling or subtracting these 2 attention maps, the diff transformer outperforms the transformer in various settings for scaling up model size and training tokens. So whenever you hear an attention map, you should be thinking of this, right? So this right here is the attention map, right? These are the attention kind of layers, right? So you have your Q, your Ks, and your Vs, but whenever people talk about the attention map, you should think of it kind of like this, right? And transformers, what they do is they perform this attention mechanism between the input sequence. So you see here, this sequence up here, sequence of tokens, is the same as this sequence here, right? You're basically just calculating the attention between every single token in a sequence with every single token in the same sequence. And whenever people say transformers have a quadratic computational cost, what that basically means is that this is a square, right? That's where the quadratic comes from. The longer your sequence is, the bigger the area of this square is. And every single one of these little squares is costing you some compute, right? So the area of this square is roughly equivalent to how much compute you're going to have to do. So if you think about it, the less of these squares that matter, the less compute you have to do. So if we could get rid of a lot of this square, right? If a lot of this square was basically just white, which in this case means the attention is very low, right? So the attention score between the word the and the word film here is basically 0. So if you're doing full attention and you're calculating every single one of these attention scores, you're basically at one point, your GPU is just calculating 0 times 0, right? You can think of it like that. You're wasting a bunch of compute just multiplying this very small number by this other very small number. So what we really want is we want this to be sparse, right? And what sparse means is that there's only a couple squares that matter here. And differential transformer, pyramid drop, and this paper that we were reading here, what matters in transformer, are all kind of coming to that same conclusion that like, hey, really most of this attention map is kind of just a bunch of zeros that don't matter, and we're wasting all this compute just multiplying zeros by zeros. If we could figure out a way to only use kind of the couple points that matter here and only calculate those, then we can drastically speed things up. These guys do it by dropping layers, right? And this What Matters in Transformer paper. The differential transformer is a little bit more complicated, but it's basically the same idea. It's like they're taking the difference between two of these, and then they effectively get a sparse attention pattern. And then in this pyramid drop paper, they drop it also, but this is for a different modality. So, and that's also why I wanted to show this paper, right? Because this paper is only about Llama 2 70B in the text modality, right? So it could just be that these sparse attention maps are only a property of text-based models, but this paper proves that that's not the case, right? Pyramid drop shows that this is also happening in vision models. In fact, it's not only happening in vision models, it happens even worse in vision models. So vision models are even more prone to like a bunch of empty 0 times 0 kind of calculations in the attention map. Welcome back to Course Find Stuff. How's it going, Cheb Khaled and Aaron? This makes sense, but I wonder how it performs. It performs really well, right? So I think in all of these papers, they show empirically that, yeah, you can drop a bunch of the, in this case, attention layers, and then in the pyramid drop, they actually drop entire tokens. And it still performs really well. So let's read a little bit into this pyramid drop, and then we'll go look at the figures for both of these. So in pyramid drop, they're going to be doing an empirical study revealing that all visual tokens are necessary for LVLMs. And the vision language model world still hasn't settled on a single term. So sometimes people call these VLMs, MMLMs, so multimodal language models. Here they're calling them LVLMs. So all of those really just are different words for the same thing. In the shallow layers, and token redundancy progressively increases in the deeper layers of the model. So what they're saying in this paper is that actually the amount of redundancy is dependent on the depth of the layer, right? So here, the layers that are closer to the input, these are the shallow layers, and the layers that are closer to the output are the deeper layers. So what they're saying is that actually, as you go further up this pyramid, in this case, we're going down, so it's a little bit counterintuitive, but usually this figure is upside down, right? So this would be the lower layers or the shallow layers, but here it looks like it's at the top. But at the bottom of this pyramid, you can have more, as you go up, the sparsity actually increases, right? So what they're going to be doing in pyramid drop is they're going to be cutting this visual transformer, this VIT, into several stages and drop part of the image tokens at the end of each stage with a predefined ratio, creating pyramid-like visual tokens across model layers. And this is a inductive bias that has been kind of baked into architectures before, right? If you really think about what a convolutional neural network is, it's baking in this inductive bias that as you go up from the bottom layers to the top layers, you should have kind of less of them, right? So there's a lot of model architectures that have this kind of baked in. In a VIT, it's not really baked in at all, right? Because the vision transformer, you're just repeating the same blocks, and you're not baking in that assumption that, okay, at the top, you don't need as many blocks, or you don't need as many tokens. So Here, what they're doing is they're kind of taking the visual transformer, they're turning it more into kind of a convnet in that way. Okay, and in terms of numbers, they get a 40% training time and 55% inference flop acceleration of Llama Next. Llama Next is a vision language model created from a llama model, and it's a very popular way of creating these vision language models where you basically take a language model and you take a vision encoder and then just basically glue those together and do a little bit of training to train this little adapter layer that basically glues those together. Okay. Images exhibit substantial spatial redundancy but are difficult to compress losslessly. Excessive image tokens and a steep increase in training and inference costs. So what they're saying here is that most images have a lot of redundant visual tokens, right? If you take this image and you turn it into a sequence of tokens, which is what you're going to have to feed into a transformer, there's a lot of unnecessary information in there, right? Think about how many tokens are just sky token, and you're just saying sky token, sky token, sky token, sky token, sky token, sky token, right? Like at some point you kind of get the point. There's a sky in this image. You don't need the sky token 7 million times, right? And whenever you think about the corresponding attention map for this, right? Like think about taking this right here. Sorry, nope, this one. Every single one of these little sky tokens there's an attention score that's being calculated between sky token number 3 and sky token number 4, and then sky token number 4 and sky token number 2, and then sky token number 2 and sky token number 5, right? Just like all of that is wasted computation. You don't need to be doing attention scores between all these different visually redundant tokens here. Okay. The number of image tokens increases quadratically with the resolution. So not only do you have the quadratic curse when it comes to the fact that transformers have this quadratic attention, but then images themselves also have a quadratic curse where as the image resolution increases, the total volume of the image tokens inside increases quadratically too. So you're like double shooting yourself in the foot when you're feeding an image that is progressively higher and higher resolution into a transformer that is progressively larger and larger, which is the trend. Okay. Removing different ratios of image tokens at different layers on the LLVLM at inference time, which is what they're going to be doing here. Sensitive towards token dropping on shallow layers. In deeper layers, image tokens gradually become less critical to the final results. So they introduce pyramid drop, a simple yet effective image token reduction strategy, dropping a portion of the image tokens at the end of each stage according to a predefined ratio. And that's the only thing that's a little bit sketchy in this paper is that they basically hard code these ratios. So as you move into higher and higher in the layers of this lava vision transformer, you basically drop more and more tokens. Okay. Let's look at these figures because I think the figures are what really kind of drive this point home for both of these papers. So we have here observations, little typo for you guys. The preserved image tokens are those that receive the highest attention from the text tokens. Okay, so you look here, you have an image of a bus, right? And in a vision language model, you put in text tokens, and then the image tokens get added, right? And the image tokens and the text tokens are both part of the input sequence, so they can pay attention to each other, right? So you can look at the attention scores, and this is also another reason why transformers are popular, is that you can use these attention maps to actually get a little bit of explainability, right? So when you're looking at a multi-layer perceptron or a feed-forward network like this, it's a little bit less explainable, right? You're just seeing this giant mass of neurons, and some of them are activated and some of them are not activated. It's kind of difficult to know what the hell you're looking at. But with transformers, a nice little kind of feature is that you can actually look at the exact tokens that have high scores. So here, for example, when you ask, what is the bus's license plate number? You can say, okay, at layer 2 in the shallow layers, which tokens are actually getting activated here? And you can see it's these like text tokens here, the tokens, or not text tokens, but the tokens that are representing kind of text around the bus. And you can see there's a little bit of a notion of like, okay, it kind of seems to be paying attention to this here, this here, this here. That's kind of explainable, right? As you go higher up into layer 16, now you can see that actually the attention map becomes much more sparse. It's really not looking at almost anything. It's really focused on just this front part of the license plate. So as you go higher up, right, from layer 2 to layer 24, the tokens that matter become a smaller and smaller percent of the total tokens. You have a more concentrated distribution of attention scores. So that's useful to us because it means that we can get rid of all this other crap, right? So all this blue is computation that we could be throwing away and thus improving our inference speed. So let's go back to this paper, because this paper does find something interesting here. And we're going to look at this figure here. So here they have a figure that says the importance score for MLP and attention layers. So the importance score is basically their own little kind of metric here that determines how important is each individual layer in terms of the actual final performance. So in this paper, right, they're cutting random parts of the transformer out. They're basically ripping out chunks of this brain, and then they're seeing how important was that chunk of the brain to the overall performance of the model. And one interesting thing that they note here is you can see that for the multi-layer perceptrons, there's this kind of effect here where the first layer is very important and the last layer is important, but the middle layers are kind of garbage, right? So a lot of these middle layers, like if you cut out block number 23, you're going to get better performance than if you cut out block number 1, right? If you cut out block number 1 or the MLP in layer 1, and if you cut out the MLP in layer 31, those are kind of important, right? But if you cut out these layers in the middle, they just don't really seem to matter that much. And there's also this kind of gradient here as well, right? So like the earlier layers matter, then they matter less and less and less, and then those last couple layers matter, right? Same thing here with the attention layers. So you have a similar kind of effect where attention, much like the MLP, is the attention layers at the beginning and the attention layers at the end are a little bit more important than almost like the attention layers here at the very end are the least important, right? So one way of thinking about this is that the beginning part and the end part are the most important parts of these deep neural networks, right? So let's go here. Block drop, MLP block. Let's go back here into this figure. Okay, so now we have another figure in the pyramid paper where overview of pyramid drop. We divide the forward pass of the LLM into multiple stages and drop parts of the image tokens at the end of each stage with a predefined ratio. So you see here's the very beginning of the process, right? So you have your text tokens, which you typed into the computer, that's getting turned into some text tokens here. And then you have your vision token, your little vision encoder, which is receiving this image. And the vision encoder in this case is it doesn't need to be a VIT, but usually they're VITs. And it's going to turn via this projection or adapter layer that you train in this lava style VLM into a bunch of vision tokens, right? So you're basically turning this image into a bunch of vision tokens, and you're turning this question into a bunch of text tokens, and you're basically concatenating those. So what the actual intelligent pre-trained language model inside a vision language model is seeing is really just this sequence of tokens that's just concatenated text tokens and image tokens. And they drop some of these, right? So you see at the very early stages or the shallow layers, you have a low amount of drop. So you're only getting rid of maybe 50%, it seems, of these tokens. But even still, you can see that it's kind of focusing on the important parts here, right? So you're just asking who is standing on the dining table, right? So the answer is that the mouse is on the dining table. And you can see in the beginning layers, you're kind of dropping all these redundant visual tokens here of the background and the sky. And then as you go higher and higher up, right, you kind of more aggressively drop. And you can see that really you're only focusing on the important parts. And all this other stuff here, this is saved computation, right? You're saving memory and compute by not calculating that, right? And you can actually see it's a very similar kind of situation to this, right? Where early on, you can drop more, and then as you go to the end, or early on you drop less, and then as you go to the top, you want to drop less, or drop more. So here you go. More aggressive pruning at the top, less aggressive pruning at the bottom. But one thing that they don't do in this paper is they don't deal with that last layer effect, right? So it seems to me, based on this paper here, that the last layer is quite important, right? And I think they have another figure here that shows you that it's not a uniform gradient, right? So it's not like the first layers and then it just kind of continuously goes down. There does seem to be this last layer effect, which in this paper they just ignore, right? Because in this paper, they're only doing it based on a predefined ratio. So it's like they're just, they have this inductive bias of a pyramid, right? And the pyramid at the very top is the thinnest. But really what you want, it seems like, is a pyramid where the last layer is also thick. So it's like a hourglass pyramid. It's like a hourglass where the top part is like very thin, I guess. I don't know how to describe it, but it's not quite a pyramid. Here, I guess it's kind of like a pyramid, right? But you still have a little bit of that last layer effect. Okay. Yeah, this is more what you want, right? So this is inside the first paper here, or the text paper. Yellow areas represent the retained layers and red areas indicate the dropped portions, right? And these guys are not doing it on a predefined ratio. These guys are doing it based on a similarity score. So they're actually looking at what's coming in and out of these layers and then deciding based on a similarity score which is worth dropping and which is not worth dropping, right? So you can see that in the very early layers, you're keeping everything and then you drop more and more and more and more and more. And then the last layer, you don't really want to drop. You want to keep most of those because those are all mostly similar, right? So you have this kind of like weird, like up and then down, up and then down, up and then down. And this is not specific to any of the types of dropping, right? They did 3 different types of dropping in this paper. They did dropping entire blocks, dropping the feed forward or the MLPs, and then dropping the attention layer. So regardless of whether you're doing attention drop, MLP, or block drop, you see this same pattern, which means to me that's like a meta pattern. It works regardless of the architecture. So I feel like that should also be the case here. But in this one, they don't quite do it like that. Okay. It looks like QR codes. For different Sky tokens, let me see, I'm reading the chat here. There are n encoder decoder blocks. Maybe there's a redundancy for one encoder decoder block to the subsequent. I think these are decoder only transformers, but in the vision case, you do have a vision encoder. Can we do this as pruning aware training? Pruning aware training is a little bit different, but it's a similar kind of idea, right? Where you're basically realizing that a lot of the computation that you're doing within this giant model is kind of redundant and unnecessary. Okay, there's another effect here that I thought was kind of interesting. And here we're going to kind of build to it, but look at this. So we have a Lava Next 7B, which is just some vision language model, right? And they are comparing the vanilla version of it versus the P drop, which is their pyramid drop, right? So you can see that for example, the number of GPU hours required to train, it actually gets significantly lower, right? So whenever you drop a lot of these visual tokens, because of the quadratic computational cost of attention, the more tokens you drop, the less it's going to take to perform inference, to perform backprop, to do all of that stuff. So you can see that you can train stuff faster, right? It's still the same number of patches, because at the very beginning, you're turning your image into these patches. That's not changing, right? But look at the drop in inference budget. So inference flop is basically how much compute you're spending at inference. You can see that it's almost a 2x drop there. And then these are a bunch of benchmarks. So they're saying, okay, we basically cut out half the brain. How does it perform? It performs pretty much just the same, right? 67.4, 67.3. So you cut out 50% and it's performing about the same. So that's pretty good. But then here's the magic part. Look at this one. Lava Next 7B, vanilla 483 GPU hours, 269 GPU hours for the P drop. Look at this, 64.4 versus 63.5. So in this case, you cut out half the brain and it actually performed better. So that's even crazier, right? Because we're not just talking about like, hey, I basically reduced the inference budget, but or inference computation and training computation, but it's going to be a little bit worse, right? It's not just a little bit worse; it's actually a little bit better, which is kind of crazy to think about. And there's evidence of that in this paper as well. So here, in this figure, they look at the performance with respect to dropping ratios. So the solid lines represent the impact of dropping the modules. So you can see that the layers that you drop at the beginning versus the layers that you drop at the end, right? You have the kind of this same effect on all these different benchmarks. So this is the performance on each benchmark. But look at this one here. In the attentions drop, right? So we're cutting out attention layers. It's above this dotted line, which means that actually when you drop some of these attention layers here, you're actually increasing the performance on OBQA. So I don't know, I thought that was, these two right here, those two are very interesting results to me, where it's like basically, it's not just, you're not just reducing the performance a little bit, you might even be improving the performance in some situations. So you can actually have a model that becomes smarter when you prune it or drop a bunch of it, which is non-intuitive, right? That actually goes against this kind of like scale is all you need kind of bigger models mindset, because this is telling you that a small model is actually beating a bigger version of that same exact model, right? And that's kind of what these guys are saying in the differential transformer, right? It's not just, hey, we're going to create these sparse attention patterns, so we're going to be able to perform inference faster, and we're going to be able to use less training budget, but it literally outperforms the transformer. So we can actually get better performance by cutting things out, right? Okay. Visualization of important scores. During the pre-training process, where lighter areas represent low importance scores, i.e. high similarity. So high similarity means that a lot of the features that are going into each of these layers are basically the same feature, so they're redundant. So they're going to say if there's a lot of redundancy, a lot of redundant features, you're kind of just feeding it a sequence of the same shit over and over again, then that means that each individual feature is of low importance. So here in the early layers, it's more yellow, which means that most of this is just kind of repeating the same thing, right? So as kind of in our way of understanding this is that there's a lot of these sky tokens, right? There's a lot of the same sky tokens over here, sky token, sky token. So like each individual sky token is low importance, doesn't have a lot of information. So you can be more aggressive about the cutting and pruning. But as you get higher and higher up, especially with these MLPs, right? The MLP and the block are the most pronounced here in terms of this first and last effect. Which kind of makes sense, right? Because the very last layer is the one that basically creates the representations that are ultimately used to do your output, right? So at the very end, right, you're going to take the sequence of features that's coming out of your stacked blocks, and then you're going to effectively use that to classify the next token. So you're basically trying to say, okay, this next token that I'm going to auto-regressively predict, which of whatever 100,000 possible tokens is it going to be? Which word is it, right? So it's kind of like a classification problem. So intuitively, it makes sense that the very last layer is probably kind of important. If you start dropping out too much shit here in this last layer, like you're going to lose a lot of performance. Reminds me of your transformer is secretly linear paper, also pointing out the redundancy of the attention in the middle blocks. Yeah, and maybe another way to think about, right, all of these papers are pointing to this fact that, hey, these transformer models have a lot of redundancy and we can cut them aggressively. But maybe that's also why the transformers are so powerful, right? So like transformers work in almost every single modality, every single type of problem that you can think of. You just use a transformer and it kind of works. And part of why that might be the case is because they are redundant, right? So if you have a model architecture that has very little redundancy, then finding the correct set of weights that solves some kind of problem, right? Like whenever you're training, what you're really doing is you're moving around in the kind of space of possible versions of that model using gradient descent to try to get to a point where you're minimizing some loss, right? You're trying to get a smart model by just changing it little by little over time, right? You're moving around in this loss landscape. If your model is very, very redundant, which is what transformers are, then there's a lot of ways for the information that is important to kind of get to the final location where they make a difference here at the very end. So I think the fact that transformers are very redundant is the reason why they're so good on such a wide variety of modalities and domains and problems, is because there's so many different paths for the gradients to flow and then for the information to kind of bubble up in the right way, right? And this is something that you used to kind of explicitly regularize for, right? When you think about dropout is a technique that was very popular whenever people were just training very deep multi-layer perceptrons, right? Like kind of classic deep learning. You would do this technique of dropout where you would basically randomly kill half the neurons during training. And what that resulted in was the each individual layer, right, had to learn to basically duplicate stuff and information so that if it happened to get killed in that particular batch, then the information would still have another path to go through, right? So like dropout is in a way promoting this kind of redundant information so that it's more robust to that zeroing out that you do when you do dropout. And transformers just kind of have that in there, baked into the architecture with this quadratic attention map. One interesting thing that I saw here, specifically in this paper, this one here, is, okay, as we're going up in these layers, right, in this vision language model, we're seeing that more and more of these visual tokens are redundant and we can get rid of them. But if that's the case, then why is there still some sky tokens, right? Like, why is this sky token still there, right? Like, what the fuck could this sky token possibly be doing to answer this question of the year, right? It's trying to find this, it's trying to basically do OCR on this very top little part here, right? So it doesn't make any sense that like this very corner token over here is in any way contributing to this. And I feel like we've seen this many times before, and you guys have probably heard me talk about this before, but this is basically the VIT registers, right? And this has popped up in a couple different papers now, but people are basically realizing that these transformers are so smart that they learn how to sneak information in unrelated parts. So they understand that a lot of these tokens have very little information and you don't really need them, but packing in the information about this beetle into just the visual spatial area of the tokens of the beetle is maybe not enough and not redundant enough to actually get the information through. So they start putting information, sneaking information into some of the other more useless tokens, right? And this paper, I think, made the most clear example of it, where you can see, look at all these high activations and these kind of like almost unrelated parts of the image. Well, that's really the transformer figuring out a little cheat code where it's packing information. And we saw the same thing in the Llama movie gen paper that we read, where they ran into this as well, where they were noticing that their video generation model was packing information into the top left corner here, right? So it's almost like passing this semantic token, right? It's like packing a bunch of information into these tokens in the background. And I think that's what you're seeing here as well, right? So like these tokens right here, these are all, it doesn't matter where they're spatially located, because really the information that is being passed through there is not information on what's actually there spatially. It's about the fact that there isn't anything there spatially, so the transformer is kind of just sneaking information in there. An early sign of AGI breaking containment. Yeah, I don't think it's like, maybe my use of the word like sneaking in information kind of unnecessarily anthropomorphizes each individual transformer block. Like, it's not like each individual transformer block has like some kind of agency and like self-aware. It's not like it's actually choosing to sneak in information there, right? It's like it's more like it's emergent, right? Like that type of behavior is just emergent, right? Because you could think of it like one time you were feeding it batches of data during training, and then it just happened to have information here that ended up being useful, and a bunch of the other ones got dropped out. And then it just so happened that because that information was there, it ended up getting the correct answer in that one batch, which means that as you push the gradient, it reinforced that connection, and then that kind of continues to go on and on and on, right? So it's almost more like it's not the anthropomorphic. It's kind of more of an emergent behavior that's just kind of like inherent to the way that you're training this thing. AGI. We're already at AGI. I'm just going to start saying that, dude. I'm not afraid to say that AGI has been here since 2022. I think ChatGPT was AGI. I've said that on many other streams before, but AGI, the definition of AGI is general intelligence, and the generality of pre-trained language models is extremely apparent. They're so good at so many different things that is the definition of generality. If you want to talk about ASI, okay, now we can start to think about, are we there yet? And I would even say that ASI, we're kind of already there yet. We're kind of already there, but not across everything, right? There's definitely still a lot of domains where the humans are better. But I think a lot of people have started to conflate AGI and kind of like agency. To them, AGI just means, is this thing agentic and can it do all tasks autonomously? But I think that's a separate thing than AGI, right? So it's almost like AGI has just kind of absorbed all these other requirements that weren't there before. Okay. All right, let's go to this paper because I think this one's interesting too. So this is the 1-bit AI Infra. And this is kind of completely different from the ones that we just looked at. In this one, they're looking at 1-bit large language models, right? And they show, this is not really like a scientific paper, you know what I'm saying? They're just I think they actually have a bunch of other papers as well. So you can go to their GitHub, and you can see here it's like a continuing research project, and I think they have a bunch of papers. So this is just the latest of all the papers, right? But if you actually look at this paper, it's like 4 pages, right? So it's not like this is introducing the concept of 1-bit large language models. There's lots of papers that have kind of done that. This is just kind of a random, more recent paper about it, but it has some interesting numbers here. So specifically, they create a set of kernels to support fast and lossless inference of ternary bitnet B1.58 LLMs on CPUs. And this is the important part here. You get up to a 6x speed up on x86 CPUs, and then a 5x speed up on ARM CPUs. So CPUs generally fall into kind of 2 different types or kinds, if you want to think of it that way. You have x86, which is kind of like your Intel CPUs, and then you have your ARM CPUs. So that's what's inside, for example, my AGX Orin cell phones are also ARM CPUs, but there's also lots of different types of ARM CPUs, right? So ARM CPU made by like the Qualcomm versus Apple, like there's, even within ARM CPUs, it's not like there's just one type of ARM CPU, right? So there's really like families of different types of CPUs. But let's look at here. What am I trying to look at here? More flexibility, higher efficiency. Your CPU has many different cores, and those cores can do a lot of different things, right? And each of those little things that it can do, you could think of it like a kernel, right? So the kernel is basically like a little algorithm, and your CPU has a set of these kernels that it can run, right? So here's the 100 different little things that it can do, right? And each of those little things is a kernel. The GPU, slightly different than a CPU, is more about doing a reduced amount of things. So there's less things than it can do, but each of those little kernels or each of those little things that it can do them in parallel. So it can do like 1,000 of those at one time, rather than the CPU, which is kind of doing like one at a time. And then FPGA, ASIC, that doesn't really matter. This is kind of more where you're getting into the space of like, okay, this is very specialized for a specific type of compute. So you know exactly the 4 things that this computer is going to be doing, and you design the actual chip such that it really only does those 4 things optimally. Versus a CPU, right? People use them for thousands of different types of things. So they need to be a little bit more flexible in terms of the amount or the different types of kernels that they can support, right? The different types of little algorithms that they can do, right? And what is the most important thing when you're doing any kind of AI or deep learning workload is basically matrix multiplication, right? And you can do matrix multiplication on any of these, right? But fundamentally what matrix multiplication is you have this big matrix of matrix 1 and then matrix 2 here, A and B, and you have to basically multiply each of these things and then add them, right? So when you really think about what a matrix multiply is, it's a bunch of, okay, I need to get this in whether you're using a CPU or a GPU or an FPGA or an ASIC, you basically have a little part of that chip that's actually performing the calculation, and then you have a little part of that chip that's storing the information, right? So you kind of have this same idea of like there's the memory, and then there's the thing that's actually doing the thing, right? And that is kind of fractal in a sense as well, right? Where we like to think of the CPU, and then you have your RAM, and then you have your GPU, and you have your GPU VRAM. But even within the GPU, you have different layers of those cache, right? And then within the CPU as well, right? So you have little tiny chunks of memory that are even closer to the little CPU cores, and then you can even fractal deeper into that, right? So the core idea is that you need to retrieve numbers or look up things in order to multiply them and then store them back. So you're like basically grabbing this little square, grabbing that little square, multiplying them, and then putting the answer somewhere. And then grabbing this little square and grabbing this little square, and then multiplying them and putting the answer somewhere. And then taking those little answers that you put over there and then adding them all together. And then now you take that answer and you put it somewhere else, right? So you're fundamentally just retrieving things, multiplying things, or performing some kind of operation on those things, and then storing them somewhere else, right? And if we go back here, what they're doing here is they're basically designing these kernels that allow for very fast and efficient matrix multiplication on a CPU, right? So they have 3 different kernels here, I2S, TL1, and TL2, and these are just kind of like names for those, but it doesn't really mean anything. So for example, this first one here, the I2S kernel transforms each full precision weight into a 2-bit value to save memory and bandwidth. Okay, so what does that mean? So each of these little neurons, right, has some value, right? So if we like hover over something like this, let's see if we can get a MLP weights. Can I like click on this? Okay, but there's some float number here for each of these weights, right? So one of these weights might be like 0.14345544, right? And if you're using full precision, right, maybe 16 or 32, you have to store a bunch of numbers to store that very long 0.123455445, right? In these papers, these bitnet 1-bit papers, rather than storing that very long kind of precise number, you're storing a very rounded version of that instead, right? So rather than storing 0.1444, you're storing the number 1, or you're storing 0, or you're storing -1. So you're basically saying, okay, all the weights in all the parameters in my model, I'm basically just going to ignore the fact that they're some very precise little float number, and I'm just going to store them as like a 1, and store them as a 0, and store them as a -1. Like, why do you do that? Well, because when you're performing this matrix multiply, right, if you have to retrieve a number that is represented by 32 little bins in your computer, that's going to take longer than if you have to retrieve a number that's just like stored in 2 little bins, right? So the smaller you can make the size of each of those little bins that you store the numbers in, the faster every single part of this is going to be. And at some point, you're going to get to the point where even though the CPU, right, is doing everything kind of one at a time, right? The CPU is kind of doing it like sequentially, like 1, 1, 1, 1, 1, 1. GPU is kind of doing like 10, 10, 10, 10, 10, 10, 10. So if you make the 1 fast enough, right, they're like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, then you can almost do it competitively with a GPU. Not quite, but close. Transforms the weights back to their original values, performs the vanilla. This is a matrix multiply. or matrix vector. TL1 transforms every 2 full precision weights into a 4-bit index and performs LUT computation. So this is a lookup table, right? So every 2 weights, right? So you're going to be performing some kind of multiply between 2 weights. So this little box here and this little box here, right? Well, if you already know that each individual little box only has 3 possible values, right? It only has a -1 or 0 or 1, then you don't even need to perform the little calculation anymore, right? You can say, okay, well, if I retrieve and one of the weights is -1 and one of the weights is 0, I'm going to put the answer to that in this little box over here. So I don't even need to perform the multiply anymore. I now just need to look up this number, and depending on what each of those 2 numbers is, I can just go to a different table where I already pre-calculated all the possible values of that, and then I just grab that instead, right? And here's a little bit more information or context on lookup tables. Lookup tables are excellent techniques for optimizing the evaluation of functions that are expensive to compute and inexpensive to cache, right? So inexpensive to cache, that basically means that, like, hey, I got a ton of memory in my GPU or my CPU I can just store the answers there. And then rather than having to calculate the answer every time, I just look up the answer, right? And that's where the idea of the lookup table comes from. For data requests that fall between the table samples, the interpolation algorithm can generate reasonable approximations by averaging nearby samples. And this is like an idea that is even older than computer science, right? If you, even back in like the 1600s and the 1700s, right? People who were doing navigation, or if you wanted to calculate the cosine of something or the tangent of something in the 1700s, like, you weren't going to multiply shit by hand, right? Like, what you did is you bought these like books that basically had these tables, and you could say, okay, well, here's my number 1, here's my first number, here's my second number. I'm going to go to this table in this book, and I'm going to like look at this number, and boom, there you go. There's the little calculation. So before people had computers, people were already using this idea of lookup tables to basically compute things faster, because writing a bunch of numbers in a book is very inexpensive to cache, but it's expensive to compute. So like, if you're some guy in the 1700s, calculating 2 float numbers together and getting the like cosine of that is very expensive to compute, because you literally have to do it by hand. But it's very inexpensive to cache, because you can put all those answers in a book and just put the book in the corner of your room, and that's not taking up any space at all. So this is a very old idea. But let's zoom back out, right? So why am I talking about this at all, right? Like, why is this important? Is because this is a completely separate thing from this, and these things stack, right? So it's kind of like, in a video game where you have like one item that gives you like a 20% attack speed buff, and then you have another one that gives you like a 20% attack speed buff. They don't just like add together, they stack together, right? So like, you're getting 20% on the 20%, right? It's the same way that money and finance works as well, right? Where if you have $100 and you make a 10% increase on the $100, the 10% next year is on the $110, not the $100, right? So when I look at both of these papers here, and I see, okay, I have 2 papers here that are telling me that we can get rid of 50% of the layers in these, specifically the attention layers in these transformers, and get a 48 or 50% speed up with just a 2% performance drop. And the 2% performance drop, by the way, is not even a 2% performance drop, because we have evidence that sometimes it literally helps, right? So we have the evidence that, like, hey, sometimes this is literally improving performance. So we have a 50% speed up coming from just the recognizing the redundancy in the attention architecture of transformers. And then on a completely different path, we have, hey, when we're actually performing the computation required to get an answer or perform inference with this AI, by being clever about the size of the models and the way that we're actually performing these computations on these different types of computers that we've created over time, we can get a significant speed up. So if you combine these things together, I think we're moving into a world where you're going to be able to have very tiny models that are very efficiently being run on tiny systems, such as here, I guess the Apple M2 Ultra is not really tiny, but compared to like a big GPU, that's pretty small, right? Like, and here's a little theory. Let me take a sip, answer some questions, then I'll talk about this 1 second. Okay, so here's my kind of crazy theory on this, is that I have one of these computers, right? Or one of these GPUs in my Linux PC. It's a GeForce 30 series computer, or 30 series GPU, right? Whenever these things were designed, GPT hadn't come out, right? These things began shipping in September 2020. Like if you went and you talked to the NVIDIA engineers that were designing this RTX, they were mostly thinking about gaming or maybe crypto at this point, right? They were like, okay, yeah, people are just going to use this for gaming. And here we are in 2024, and you can run, which effectively AGI on this computer, right? Some people would say, okay, we don't have AGI, blah, blah, blah. But if you ask someone in September 2020 and you showed them ChatGPT, they would say, this is AGI, right? If you showed them some tiny Llama 3 and you put them in front of a text terminal with a Llama 3 1B, and they said, what is the capital of Paris? And then they said, how many toes does a sloth have? And it answers both of those questions correctly. They'd be like, holy shit, this is AGI. And they're like, what is this? What is this even running on? And you're like, it's running on a NVIDIA 30 series. They'd be like, what? So you're telling me we already have the hardware to run AGI? And you just look at them and you'd be like, yeah, that's where it's at, right? Where there's this kind of weird, almost like backwards compatibility where technology that was made before we had AGI is capable of running AGI. Right? That's fucking crazy. The fact that that's real. And I think that these papers are basically telling you that that trend is not dead. It's actually going to get even more crazy, right? So if you have a Llama, so here, for example, in Meta, you have Llama 3 1B, right? So it's like this tiny ass little model that this is not even using this stuff here, right? So like this Llama 3 1B, this is using QLoRa. I think they have a couple other techniques here. QLoRa, spin quant, right? Like those are different ways of making it smaller. They're not even looking at this type of shit yet, right? So imagine a Llama 1B with this thing here, and rather than just quantizing to 4-bit, which is I think what these are, they quantize all the way to 1-bit. I think we might be getting to a point where we might be able to run AGI or ASI on this, right? And I'm kind of memeing here a little bit, but like, I was like, what is the shittiest, oldest CPU that I could think of? Nokia 3310 cell phone announced in 2000, right? This thing has a little tiny CPU in it that seems like it would be completely there's no way you can run AGI on this. But if these trends continue, right, all these tiny transformer trends continue, like it might literally be the case. It might just be a continuation of this, right, where we get to the point where you can literally have super intelligence running on like a cell phone like this. I don't know. It's a crazy theory, but I wouldn't even be that surprised if we end up getting to that point. Okay. Lightweight llama models. This came out like literally yesterday, so I hadn't planned on talking about it in this stream, but tokens per second, you can see here, BF16, so this is full BrainFloat 16 precision. So you think of it like you have 16 little buckets that you're using to store each of the little parameters, versus these QLoRa, SpinQuant, and PTQ. Those you're storing inside you're storing each individual parameter inside 4 little buckets, right? So 4-bit. And you can go all the way down to these guys, 1-bit. It's not really 1-bit because on average you end up having 1.58 bits, right? It's not like you're actually using a 0.58 of a bucket. It's like you can only use actual little buckets, right? But on average, if you looked at the amount of storage that each individual parameter is taking, it's like you're using 1.5 buckets per parameter. In BF16, you're kind of using 16 buckets per parameter, right? That's kind of the way to think about it. But look at that, so much faster. Almost 3 times faster than using BF16. And look at the performance drop, right? So it's really just about the same, right? This one is a little bit worse here. So you're getting average accuracy of 1 for the BF16 versus like 82 for the PTQ. And PTQ is this idea of post-training quantization. And usually what that means is basically that when you quantize, you can make that quantization more specific to like some use case, right? So like, let's say you had, you wanted to put a language model in some very specific kind of like tabular data or like some kind of weird like text parsing or JSON parsing use case, right? You could heavily quantize that language model and you don't really care about its performance on hella swag or like some other random stuff anymore, right? So you can quantize it in such a way that you are saying, okay, I still want it to retain performance on this kind of data and this kind of task, and you can use that to quantize it so that it loses less performance on that task that you want, right? The key advantage of spin quant is its portability and ability, blah, blah, blah. Here, ability to operate without requiring access to training data sets. Here they're talking about quantizing based on something that's a private data set, right? So the what they're building up to here is a world where you're going to have your data on your device and the models are getting quantized such that they work well on your data on your device, right? Or they get quantized such that they work well for some corporate partners' data on the corporate partners' private cloud, right? So quantization approaches that don't require you to effectively send Meta your data in order for them to quantize it to your stuff is useful because then you can do it privately on your cell phone, or if you're some corporate partner, you can do it on their private cloud. Yeah, and even here, look at this, you're getting some of the same results. So look at that. BF16, 41.2, 41.5. So the same effect we saw in the other papers, right? Where sometimes you even gain performance, which is weird, right? Imagine like if Einstein, you like took his brain and then you like cut out a chunk of Einstein's brain and he somehow got even smarter, right? Like that's what these little numbers here are showing you, that sometimes you can even get smarter by cutting out chunks of your brain. It's kind of creepy. .58 is ternary computing, so FPGA. I mean, this is not an FPGA though. This is like you see here, they're saying a Surface Laptop Studio 2 and then an Apple M2 Ultra processor. So these are not, I would not say those are FPGAs. Can you look at addition is all you need too? It's also relevant. Addition is all you need. Let's see. Bit Energy AI. That's like simultaneously the worst name and the best name. Computation on floating point tensor multiplications, right? You don't want to be doing that. Floating point multiplication is annoying. We propose linear complexity multiplication compared to 8-bit. 95% energy cost, right? It's not just the compute budget is effectively also the energy cost, right? So like if you're spending a bunch of compute on inference, that also means you're spending a bunch of energy on inference. If you reduce the amount of compute you need for inference, then you reduce the energy you need for inference. And in today's world, energy is in some ways kind of the limiting factor, right? Like people are talking about building like nuclear power plants specifically just to have enough energy to feed these giant data centers that are going to be performing the like millions of inferences that everyone's going to want, right? It was kind of what I was opening this stream with, is that think about how many inference requests you're sending right now and realize that every single person in the world is going to have 10 times or 100 times more inference requests in just a couple years. right? Especially when you look at things like O1 or any of these other models that are like kind of even doing more inference in the background and then doing an inference to like aggregate that and then present it to you. So if we're energy limited, anything that reduces the energy cost of this is going to be pretty important. 3-bit. Okay, so they're basically coming up with their own special little... So this float 8 E4 M3, right? So what this is, this 3-bit mantissa, is basically like any of these data types. They're basically split into two different parts. So mantissa exponent B float. Yeah. So what is the difference, for example, between B float 16 and floating point 16? So here in the llama, you see how they say BF 16? The difference there is how many of the little buckets are you using to store the number versus how many of the little buckets are you using to store kind of the exponent, which is basically like 0.000001 versus 0.01, right? Like if you have more exponent, then you can basically store a very, very small number. And if you have more mantissa, that means you can store more precision on the actual number, right? And for something like deep learning, right, you don't really care about the actual number itself, right? Whether it's 0.14535444453, like each of those additional numbers isn't really going to improve the performance as much as being able to store really big numbers and really small numbers, right? So you see this trend in specialized data types for machine learning that have more exponent, less mantissa. And I think that seems like kind of what they're doing here, right? So they have a float 8 where you see how they're making this mantissa smaller and smaller. So M2 versus M3, right? So they're saying, hey, let's make a float 8 data type that has 5 exponent buckets and then 2 mantissa buckets. I hate the all you need. I mean, the thing is that it's literally not all intention is needed. Like, it actually works, right? So the reason everybody just keeps publishing papers with all you need is because, like, statistically, I bet you papers that have all you need in the title are get more viral on average than papers that don't have all you need in the title. So, you know, don't hate the player, hate the game kind of situation there, where if it works, you know, clickbait works, and that's why clickbait is everywhere, is because it literally works. So all you need is kind of like a form of clickbait. Oh, look at this. They have some nice little calculations here. The average electricity consumption of ChatGPT was 564 megawatt hours per day, equivalent to the total daily electricity usage of 1,800 families. I mean, I don't necessarily, like, I feel like these are always kind of like pseudo bullshit, because it's like they're trying to like almost like pretend like AI is like the cause of global warming, but it's not. Like, you know what I'm saying? Like, AI has so many use cases and it can do so many positive things in the world that, like, pointing out just the fact that it uses power, it's like, how much power is being used for porn? Like, how much power is being used for people like watching McDonald's commercials, right? Like, should we ban McDonald's commercials because they're just wasting a bunch of energy? Like, I think there's a lot of other things that are wasting energy that are a lot less productive for society than AI. So I really don't think that we need to shit on AI for using a bunch of power. The brain rot of AI research. Yeah, I mean, the brain rot is real. I heard an interesting kind of talking about brain rot, where when you have a collective, right, if you think about a hive mind of ants, because the ants collectively together in this hive mind have kind of a very high group intelligence, it also means that the individual intelligence of each ant is less and less important. And if the intelligence of each ant is also proportional to the energy consumption of each ant, then there's actually a kind of a pressure or a gradient or kind of an incentive for each individual ant to become more and more stupid, right? So like, if you're a hive of ants you actually don't want to have really intelligent ants because it just costs a bunch of energy. You have to constantly feed them food in order for them to be constantly using their big brains and thinking about more things. And it really doesn't matter. You kind of are better off with each ant being dumber and dumber and dumber over time. And this happens to all kind of social, kind of hive mind type species, right? So over time, each individual ant gets more and more dumb, but the collective hive mind gets more and more intelligent. Right? And there's actually a similar effect happening with humans where it's actually probably likely that if you look at Neanderthals or kind of like early humans, they were probably smarter, right? Like Neanderthals actually had bigger brains than Homo sapiens. But a tribe of humans that hive mind is more intelligent than any individual little Neanderthal, and the collective intelligence is just more important than the individual intelligence of each individual member in your group. So that is a trend that's probably going to accelerate with AI, right? We're probably the last generation that actually had to do things by scratch and learn how to think and like store and think about things. So like if you think about a world where AI is doing everything for you, AI is thinking for you, AI is coding for you, AI is deciding all the things, it tells you what to eat, it tells you when to work out, it tells you when to sleep, it tells you what to do. You're thinking less and less and less and less. So it could be the case that as society and civilization advances, even though collectively our hive mind of humanity is getting more and more intelligent, each individual human is actually getting dumber and dumber and dumber. Yeah. And actually, not to bring up aliens and UFOs, but here's an interesting conclusion to that is that, okay, if we think about if these aliens that are supposedly coming and visiting are from very advanced civilizations, we often try to think of them as being really, really smart, right? So we say, okay, well, if an alien is coming from an advanced civilization, they're probably super smart. What if that's not the case at all, right? What if the aliens are just have been getting dumb and dumb and dumb and dumb because we're talking about thousands of years of just AI doing everything for them. So each individual alien is actually incredibly stupid, right? Because they don't know what to do. They have to rely on AI for everything. You know, so whenever people have interactions with aliens, they're like, oh, they're like kind of like almost like autistic, you know, they like don't say anything. They're just kind of like blindly staring and they don't really know what to do and they're kind of slow. What if that's just because they're not very smart at all, you know? And like if you take them outside of their spaceship and they don't have the AI that's telling them what to do, they have no idea what to do. All right, enough aliens. The ones visiting us are their AI. Yeah, the real aliens are just brain rotting inside some kind of like immortality tube in their home planet. Have you checked the Learning at Home HiveMind repo? I do not know what that is. The Symbian? That's like some kind of sex toy, right? That'd be kind of weird to have sex toys with AI built into it. This sounds kind of creepy, to be honest. AGI is superhuman. Yeah, and in many ways, it's like I already feel this myself, right? It's like whenever I'm writing code now, I feel like I'm using less of my brain. Like whenever I used to write code like 5 years ago, right? Like I actually had to think about so many more things. I had to like keep all this information in my brain and like think about how it was all going to fit together versus now coding is actually it's easier, but that also means that I'm just not thinking a lot. You know, I'm like, there's a lot of just sitting there, copy pasting, just being like, yeah, sure. Yep. Okay. Enter, tab, enter. So it's like the complexity of coding is actually, it's like a lower IQ activity now. And like, that's going to happen to everything, right? Once you have AI and everything, then like every single activity becomes just like sitting there and like hitting a red button being like, yep, that looks good. Yep, that looks good. And then at some point, if you have an entire generation of people that like they never actually had to think about anything from scratch, that means it becomes vestigial. They don't think about anything from scratch. And then think about an even more advanced version of that where you have a AGI or a superintelligence that can run on a tiny little CPU, and that CPU is in your brain. So you have a little chip in your brain that basically has all the answers. And then the neurons that are connected to that chip, they're constantly being used, right? So the neurons that are connected to that chip just get stronger connections over time. They become more robust. And all the neurons in the other parts of your brain, they start to atrophy, right? Because over time, you're using them less and less and less and less, right? So like there's going to be a neuron that's kind of connected to the fake chip that creates audio, and then there's a neuron that's actually connected to your ear. And if you start spending years and years and years inside these virtual worlds where you're only really using the audio that comes from the chip in your brain rather than the audio that comes from your ear, the neurons that are connected to the audio that goes into your ear are basically going to atrophy over time. So at some point, your brain just basically becomes the neurons that are just connected to that chip, and that's pretty much it, you know. And then maybe like the lizard brain. So it's like you kind of lose your whole neocortex, and you just have your reptile brain right on top of this chip, and there's just like one giant thick kind of cortical column that connects both of those. I don't know. I'm not a neuroscientist, so like some of those words might be incorrect, but we're close to that. Symbian is a toy. The OS is Symbian. Risky Google of the day. Symbian. Ah, okay. Mobile operating system in 1998. Released exclusively on ARM processors, although an unreleased x86 port existed. Noticeably less popular in North America. All right. Let's see what else. Course defined. The 3% we lose in performance might be tasks that need bigger transformers. The actual brain chips have an antenna through both hemispheres of the brain. Yeah, I think the actual Neuralink chip brain, right now they just connect to the motor cortex, right, which is like this fat strip right in the middle here. Right? Because they want to control a mouse, right? So right now, the Neuralink is basically just right in the part of the brain where you send commands to your hands, right? So like, for example here, like whenever you're moving your arm, you're basically using this little part of your brain, right? This motor cortex area, which is exactly where they put the Neuralink, right? Because they want the Neuralink they're using it to move stuff around, but eventually these chips aren't going to just be input, they're also going to be like input and output, right? So like they're literally giving you sensory information as well, right? So you can imagine that once you have to do that, you would have to basically have it come in here into the occipital lobe, and I think the audio comes in over here, I guess. I don't know exactly where the audio comes in, but right, like you'll basically have a chip that just feeds into there, right? And normally this occipital lobe, it's receiving information from your eyes, and then there's kind of like this pyramid of neurons, right, which is actually where the inspiration for ConvNets comes in. It comes from someone who analyzed a cat brain and then realized that there was this kind of like convolutional pattern, this kind of like hierarchy of neurons. But I don't think the Neuralinks that will create an image in your brain are going to come in at the lowest level, right? The Neuralinks that are inputting images into your brain, they're probably going to act at the highest level, right? They're going to basically input at the highest level of your brain, which means that your other parts of your brain will really only care about the information signal that goes through the very last layer of your occipital lobe, and all those early, shallower layers of your brain, which is where the real information coming from your eyes, because your eyes are just going to be closed because you're just in VR all day, right? The Neuralink VR, not like a visual VR that we have now, then all of those layers that are connecting your eye to the higher layers of your occipital lobe, those are going to atrophy. I don't know. All right. I'm going to end it there. I feel like I'm kind of starting to go off, veer off course here, but let's do a little summary here of what I streamed about. Okay. So today's stream was called Tiny Transformers, and it was a tiny little stream. But what we did is we basically looked at 3 different papers here, what matters in transformers. We looked at this pyramid drop paper, and then we also looked at this 1-bit AI Infra paper. And these first 2 papers, pyramid drop and what matters in transformers, basically came to the same conclusion. And the conclusion that they came to is that inside a transformer architecture, the attention layer is actually extremely redundant and kind of sparse, right? Where a lot of what's inside these attention maps is actually just empty. So right now, you're wasting a bunch of computation just basically multiplying effectively zeros, right? Like 0.0001 times 0.00001, right? It's like, there's no point in doing that. And one way to get rid of that is to basically drop them. So not perform that computation, which means that you are saving money and saving compute and saving energy by not performing that computation. And it turns out that it doesn't really drop performance, right? So you can actually get rid of a lot of this redundant computation and get a drastic speed up, less energy use, faster training, smaller model. And there's also this kind of interesting effect where these deep neural networks or transformer models that are just a bunch of these repeated transformer blocks stacked on top of each other, the blocks at the beginning and the blocks at the end are the most important. So you can actually get rid or use that pattern to know that, okay, really, if you want to prune or get rid of attention layers or MLP layers or just entire blocks in general, or in this case, vision tokens, you know that towards the top of the transformer or deeper inside the transformer, you can get rid of more of them, right? I think this figure here demonstrates it the best, right? The red is how much you're dropping, and then the x-axis is like how deep you are inside of it. So in the beginning, you don't want to drop too much, but then you can drop a lot kind of towards 3/4 of the way in. So both of these papers are basically showing us that there's ways just within the model architecture space to drastically reduce the compute required to run transformers with a negligible performance drop. And then the second paper we looked at was saying, hey, there's a completely different way of drastically improving the performance of, or not drastically improving the performance, but drastically reducing the amount of compute required to run these transformer models by basically drastically reducing the precision with which you're storing the individual parameters or the little values of each of these neurons. And by doing that and taking advantage of basically lookup tables and a bunch of other kind of computer tricks, we can now run tiny transformers on CPUs, which is also very important because there's a lot of CPUs, right? Like all those AWS CPU instances that seem like they're basically garbage. Think about all the data centers that are just all CPUs, right? Maybe we don't need to build data centers where you have a bajillion GPUs anymore. Maybe you can take all these old CPU data centers and use them for model inference, right? So this is a huge unlock because we have so much money already invested into these CPU data centers just for the original kind of internet age. So, I don't know. I think if you combine all of these papers together, we're going to be moving into a world where you could maybe do, you can maybe run AGI on really old tech or really small, really shitty tech, like cell phones, edge devices, right? So, buckle up because there's no way to block that, right? if you had to use a very big GPU to run superintelligence, then it's very easy to control, right? It's very difficult to make a nuclear bomb, so it's very easy for the government to control who has a nuclear bomb and who doesn't. But if you can run superintelligence on a Raspberry Pi, there is no way to control that, right? It's gonna spread almost immediately everywhere, and you're never gonna be able to control it. So we're rapidly moving into a world where ASI, which is like in many ways more powerful than any other technology we've created, is going to be extremely democratically spread out, decentralized. No one has control over it because it's just so easy to run on anything and so cheap. So it's going to get crazy, guys. All right, I'll end it there. Kind of a short one, but I guess we were talking about tiny things, so it makes sense to have a tiny stream. All right, thanks, Sarah, Godbuddy, Snooks, Saskia, NLP Prompter, Pratik, Twan, Sheb, Splinter Seller, They Call Me Ken, Twan, Amir, Luis, Ayaron, VR Wizard, Cheb Khaled, Julien. Thanks, everybody, for hanging out. Hope you have a great weekend, and see you guys next week.